So we're looking at frequency domain modeling.
Did I say that in the class? You gonna take me out of
We
there?
usually ask that before most of our classes, and he ends up being
Dynamics.
Hey,
So last time we looked at
we're on video.
just doing the differential equations. All right.
I can't say much right now.
What we'll do is
Last
we'll
class.
introduce. We looked at basically three components. Okay. So we looked at if you have this, and if you have a spring, right? And you apply a force here. Let's say you look at the displacement, right? So you can see that what you basically know is f of t is simply equal to k into x of t. Okay. I'm going to point out that k is the spring constant.
Mm-hmm.
All right. This is the input. This is the output. Okay. Now,
Shouldn't it be 1/2? No, I'm thinking something else. Sorry.
You thinking of kinetic?
Yeah, sorry.
Yeah, come on, dude.
Towards, at least I'm thinking.
and if you take the
Yeah.
Laplace of this, okay, we introduce something called impedance.
Impedance.
Okay. This is the force displacement relationship.
Hmm.
Again, keep in mind, I'm stressing this a lot. What is force?
Mass times acceleration. Or are you talking about like displacement?
Input. This is output. Okay. Input-output relationship. What we are looking at is input-output relationship. Always. Okay. Now, if you do the same thing here, if impedance is essentially, you take the Laplace of this, Laplace transform of this, what you're going to get is f of s is equal to k into x of s. Now, what we do is, this is the impedance here. Again, you see this is what? Input, right?
Input.
This is x of t is output, right? This is again input.
Frequency.
You got it? This is again x of s is output. The only difference is
Different domains.
different domains. Yes, absolutely. Good. So this is time domain.
Frequency.
This is frequency domain. Okay. Here, this k is called the impedance. And I need you to understand the impedance. What is the impedance for various components? This is the first component. Okay. What we'll also introduce. Essentially, whenever I do this, this is the wall. Okay. You have a damper. This is how a damper is represented, and if you subject this to a force, let's say this is the damping coefficient to C, and this is the displacement. Okay. force displacement or the force displacement relationship is f of t is equal to c into d over dt of x of t. Okay.
Does it say? So it says time domain and I can't read the second one. Something domain.
Frequency domain.
Frequency.
So if you look at this, this is the force displacement relationship. All right. If you take the Laplace of this, you're going to get f of s is equal to cs x of s. All right. Again, here c of s is the impedance. And this is the last one we are going to address as part of this lesson. You have a mass. This is the displacement. This is essentially, you understand, this is just a reference for the displacement. Okay, from this line going this way. Okay, there is a force, and let's say the mass is m, right? Keep in mind, K, C, M are constants. Okay. Assume constants. We'll talk about this. Here, f of t will be what? M d over dt of, or d square over dt square of x of t, right? Newton's law. You understand? Mass is, force is equal to mass into acceleration. Okay. And if you take the Laplace transform, you're going to get f of s equal to m s square x of s. Okay. Again, this is the impedance. So you have to understand that K, C of s, ms square is, all these are impedances here, okay? Now let's look at how to use these impedances to come up with this mathematical model of the system. And I'm going to look at the example we looked at last time. We'll do it with an example. You have this. You have a spring. You have a mass. You have another spring here. You have a damper. Another mass. And then
I'm trying to go to bed. Shut up, Torius.
this is K1, K2, K3. You have C1, C2, C3. This is M1. M. There is a force applied here,
You can get him in the little one.
F of t, and
Appears.
what you're going to see is from this reference, okay, this displacement will be x1 of t, and from this reference, this displacement will be x2 of t. You're with me? How to figure out now what we always want to figure out is this force displacement relationship in this domain now.
Understand that's C1. That's the
So
why did you draw the arrow like that?
So I'm just showing that it's on a
Friction.
surface, there is friction. Okay.
Right.
So friction acts like a damper. You understand?
Yeah, but is that a C or is that an arrow?
C1.
You
This
know-
is arrow. I'm saying that's where the friction is.
Mm.
Okay. This is where the friction. This is C2. Okay. We're just naming it. That is a C3. So the impedance approach is you start with mass 1. How many other masses are there? You look at sum of impedances connected to M1.
Excuse me, Dr. Sony.
Hmm.
Is this the easier way you was talking
This is
about?
the easier way, yeah.
Okay.
Okay. Multiplied by x1 of s minus sum of impedances common to M1 and M2 into x2 of s.
So is C3 the common impedance that you're talking about? Yeah.
C3 and K2. Right?
Okay, yeah. Mm.
Okay. So sum of impedances. Now think about what are all connected to. So pay attention here, guys. Look at this. See if this makes sense. M1 S square, right? That is the first one. You see? This one. All right. Plus
What the?
C1 plus C3, right? S.
So stressed.
You with me? Guys, pay attention here. Don't fool around. C1S plus C3S. You got it?
Is it?
Plus K1 plus K2 into x1 of s. Minus, what are common? Common is C3S plus K2 equal to f of s.
Dr. Sony, shouldn't there be a K2 X1 that's negative though as well? That's coming to the other way or no?
No.
No.
Does this make sense?
Mm-hmm.
Let's see.
You see mass 1, okay? What is all connected to mass 1?
You got K1. You got
K1.
You got the force. Oh, it's not connected. That last one, my fault.
K2.
K1, C3.
So M1 is connected, right? First, you have to consider this as well.
Okay.
Okay. M1 is square plus C1S right?
Mm-hmm.
Plus C3S
Okay. AK2.
plus K1 plus K2.
Well, why do you have to add the mass in there if that's what we're considering?
No, that's just the way to write the impedance. He said like down
All
there.
impedances connected to mass 1.
I'm not gonna lie to you though. I thought that K was a different way to write CS, and I thought CS was a different way to write MS squared. But they're all different. And you see how he gave us examples, like
Right, so C, there's a S, okay.
but they're different. They're different impedances. Like
Yeah, C is, so it depends on if it's different damper, the different constants come into play,
mm,
right? It's not the same thing.
yeah,
You got it, so mass 1 and mass 2 will be different, right?
Mm.
So you have M1 and M2. Okay, so you get this?
Okay, so your M1S squared, that's just the mass, and then you have
That's the impedances.
yeah,
You look at
impedance
mass.
of the mass.
Impedance, okay?
Yes.
Then you look at this. How many dampers are there? There are 2, right? 1 and 2.
Mhm.
Or those 2. Alright?
Okay.
Then the spring, 2. All of this into X1 of S.
Okay, I gotcha. Now I'm tracking.
Minus what is common between M1 and M2?
The
Only those 2, right?
K2 and C3.
K2 and C3.
mm-hmm.
So you have CS. So what you have to do is make it a habit to write it in that order.
Mm-hmm.
In order of the polynomial. Okay. Equal to f of s. All this has to be in frequency domain. Impedances are in frequency domain. Okay. Now similarly, mass 2, it reverses. So here mass, it will be sum of impedances connected to M1 or M2
Mm-hmm.
into X1 of S.
Mm-hmm.
Minus
X2.
sum of impedances common between M1 and M2 into X1 of S.
It's X1. It's not X2. So it doesn't switch.
Right, this is X2,
Yeah, okay, and the next one's X1.
that is X1.
Okay, cool.
Okay, so if you do that, now you're going to get M2 S square plus C2S plus C3S plus K2 plus K3. Into X2 of S minus, again it will be the same thing here. Okay? It so happens that this is the same, but you have to keep in mind this is X1 of S equal to what?
Oh, the sum of the forces connected to M2.
Mhm. Equal to?
So it'd just be FS. Or you could,
There is no force, right?
oh, that's right.
Only force is here.
That's right.
So that the impedance of force is F of S. Okay. There are no forces connected to M2. You see?
What? Oh, yeah, I see what you're saying.
Okay.
Dr. Sunny.
Hmm.
I had a side note. Sorry before I forgot. Picard said he wasn't feeling well. So
Okay.
So he said just to let you know.
But do you see this?
Mm-hmm.
Shouldn't it be X? No, never mind.
Now,
Hmm.
you see how like we're pushing the blocks this direction,
Hmm.
and I'm guessing like springs are like naturally compressed, and you have to pull them out.
They are not compressed. They are in their equilibrium state.
Oh, okay.
At this, okay. There is no force. Only when you
Uh-huh.
apply a force,
Yeah.
external force, they will apply a force in the opposite direction.
So like, it would take the same amount of force to compress them as it would to expand the springs.
Yes. If you go by this, so this is what it is, right?
Mm-hmm.
When these two are equal, it's an equilibrium state. This does not you don't see compression or tension here. Do you see that? You don't see it. You just look at the force and displacement.
Right.
So it's either way.
Okay.
Okay. Now I'm going to erase this.
So you would do the Laplace transform to transform it from the time domain to the frequency domain, and then do this on the right.
All you need to remember is these
Okay.
impedances.
But if we're given
Impedances are in Laplace transform only.
yeah, but if we're given like the force displacement, so if we're given f of t kx times kxt, we would have to do the Laplace transform to get the impedance, and then we can do what we just
You
did.
have to remember this. That's all.
Okay.
I will not ask you this.
Okay, gotcha.
This is essentially the basic building blocks of your
Mm-hmm.
frequency domain modeling.
Yeah.
Gotcha. Okay. Now I'm tracking.
Okay, and you have to. So these are the basic building blocks: spring, damper, mass.
So what does impedance mean here?
It's just the Laplace equivalent.
Mm-hmm. Like a big constant.
It's input-output relationship. Okay.
So, can I
Here,
go?
input-output relationship. You see, this is input, right?
Right.
Mhm.
This is the output. So K is the input-output relationship. The force you can say is proportional to displacement,
Mhm.
and the proportionality sign is force is input, displacement is output. The proportionality sign is replaced by K.
Yeah, but is it not a physical quantity or something?
Yes, so that is the same here. Input. This is the input. This is the output.
I thought impedance was something that you can measure as well. Can you not
This is
measure?
a different impedance. This is essentially impedance is what? Resistance. It's a type of resistance. So how much is a resistance? Is this K.
By the amount of force you put on it, right?
Resistance is, if you look at, if you bring a spring, this thing, the resistance is a property of the material, right?
Yeah.
Is it dependent on input? It's not dependent on the input. It's a property of the material. Okay, so this is the property of that material. Depending, so you can say that applied force or displacement will depend on applied force, or force is proportional to displacement for a spring. Okay, so it depends on the what kind of spring you use, what is the property of the spring, what is the material, how many coils you have, how closely they are, what is the gauge of the coil.
Mhm.
All that is captured in this K. You got it? Similarly, for a damper, if you apply a force, it will be proportional to the damping coefficient will determine how, or the velocity with which you push a damper
Mhm.
will determine how much force it will apply.
Mhm.
It is not the displacement. So if you look at the spring, the displacement is purely a function of force, or force is purely a function of displacement. Here it's a function of velocity. Here this is a Newton's law essentially.
Mhm.
You got it?
Okay.
Okay. Until this point, see, this is what? This is more of a static problem, okay? This becomes dynamics because there is force involved, and then you can see that this is just some weight acting or some mass, some pressure acting on this. All right? You got it?
Yeah.
And here the impedance, equivalent impedance is C into S.
Mhm.
So here this is input, this is output. The input-output relationship is the impedance. Input-output relationship is the impedance.
And if we wanted to find it instead of with displacement, like a function of time, like for instance, with the how will we just have to solve for it like you would in the problem if we found it like f of s, and we wanted to find f of t, we could just like rearrange everything and get it.
That's what I'll talk about that. Okay.
Mhm.
So what you do is once you get this, the next step is look at this. See, if it is just one component like what you saw, it's easy to figure out the input-output relationship, right? So for this system as a whole, you have to look at these two equations together. That is m1 s square plus c1 plus c1 plus c3 s plus k1 plus k2. Okay. X of s, x1 of s minus
Screw
c3s plus k2 x2 of s equal to f of s. Okay, this is one equation. The next one is minus k2 plus you see, this is a system of equations, right? You see this as a system of equations?
Yes.
You have to look at this in terms of ax plus by is equal to this call as b and cx plus dy equal to q. You see this? This is x. This is y. Okay. A is this quantity.
What do you have it as a negative?
Huh?
What do you have it
I
as?
switched it.
Oh, okay, I see what you're doing
Okay. Because of this x1 of s. I have to write it in this form.
I got it.
Okay. So here,
there. Oh, okay, I see.
your end goal would be to find,
You got drip. I'm proud of you.
again, input-output relationship. Okay. Shift in the form of transfer function. We looked at transfer function last time. Okay. So here, what are the inputs? Input is simply, there's only one input, right? F of s. Okay. What are the outputs? It is x1 of s and x2 of s. Typically, you will be required to find, I'll say, what is x1 of s divided by f of s, or x2 of s divided by
Is that a special ratio there? Is that like a special ratio?
So you have to solve for this essentially. Okay.
Alright.
Solve for the simultaneous equations. Right? If you're given a system of equations, if you're given ax plus by equal to, let's say, z, all right? Ex plus by. And just like z1 and z2. Here it so happens there are, think about this. SISO stands for single input, single output. Okay. SIMO stands for single input, multiple outputs.
Multiple input, multiple.
No,
Multiple
yeah,
input,
cool.
multiple output. This is a
Just guess.
single input, multiple output system.
Still.
You got it?
Yes, sir.
Wait, so sorry, I didn't catch that, but it should be a multiple output system.
It will be a single input.
Input, multiple outs. Gotcha.
It is this system, okay? Here.
FFT is the only input.
Just a
Or FFS.
So here, it so happens that this is simply 0, okay?
Mm.
These two are outputs and this is input. And what you're trying to solve is you're trying to solve for either x1, either x or x2.
Either X or Y.
X or Y, yes, you're right. Okay, and it's so what happens is you'll solve for it. This z will simply come on the left hand side, and then you get that ratio. Okay, you use something called you need to use this Kramer's rule. Okay.
It sounds so familiar.
That's not the it's classified as
Kramer's rule.
linear algebra.
Oh, okay. Oh.
But you used it in linear algebra and engineering math too.
The
Before-
Kramer's
before I
rule
dropped
is
it.
what you need.
The reason
You
why I
take a
dropped
system
it.
of equations, and then you write those system of equations as a matrix,
Mm-hmm.
and then solve the matrix.
Oh, yeah. Yeah, my bad.
Okay.
That's the
You more
system.
matrices.
That's that fun.
Sure it is. I hate matrices.
Tanabe isn't good at matrices.
Tanabe is good for math actually.
Thank
He's
you.
not good at matrices though.
You're not good at matrices.
No, he messes up so much.
I made a mistake on the test, and he's
No,
blamed
he
me
made
for it.
mistakes on the test.
On the okay, cool.
You make several mistakes on the test.
I learned from these mistakes, and
Yeah.
I'm still the greatest mathematician to ever walk these school grounds. I'm decent.
Well, you're not even a mathematician because you.
Yeah, I could.
You have the competency, but you don't have the character.
Hey, I'm a great man.
First, he has to get.
I actually single-handedly solved this. Never mind. It's a long story.
You don't have the character.
Trust me. I used to sit in my room and do mathematics by myself for the fun of it.
Nerd.
Welcome to every other mathematician.
Okay, so if you have
I thought it was like, all right.
if you have ax plus by equal to z, okay, and cx plus by, I'm just going to write this as z1 and z2. Okay? What you do is you can write this as
A, B, and then Z.
d.
Z and 0.
This is
You take the determinant of it?
yes. Okay, so this is
Yeah, I remember you. Yeah, that. Then you take the determinant of it, and then you.
You don't even know what to do, do you?
Actually, I do.
Give me
What is that? D what?
dx.
Yeah.
This is d, okay?
Just D?
Yeah, you're going to solve for d, dx, then dy, then dz, and then you figure out what x, y, and z is by dividing dx over d and dy over dz. No, he doesn't remember that because he didn't stay in the whole class.
I'm pretty sure there's an easier way to do this.
No? Well, you can use elementary row operations.
Yeah.
So for if it's a 2 by 2, it's typically once you figure out this method, it's easier to solve like this. You can solve that as a set of equations, but there are 3. It starts becoming complicated.
Mm-hmm.
Okay. If there are 3, this method becomes really easy.
All right.
So your x, if you want to solve for x,
you divide it.
what you do is you dx by dt, and you solve for y, you get dy by. Does that make sense?
Then you plug those in. You would plug those in?
Right, determinant.
To AX.
Okay. So here, just remember this. You have to look at this method by yourself as well. Okay.
This
But
is
if I
called
apply this, all right, I'm just going to write this as x1 of s, which is solving for x. Okay. What I'm going to get is a and d.
Yeah. AD minus BC
AD minus BC. All right.
for D.
So I'm going to get first dx. If I do dx, dx is what? F will come here, okay? And 0 will come here. dx.
Oh, Z2 is 0, so
Z2 is 0.
that means
So you're going
it's
to get,
just Z1 times D.
right, you're going to get F of S, all right, times M2 S square plus C2 plus C3 plus S plus K2 plus K3 divided by
D. So it's going to be
this
those two.
minus this. Okay, you're going to get,
It's going to be positive though, won't it?
Hmm?
It's going to be positive though.
no, it will be negative because this is also negative.
Oh,
this
yeah,
is
yeah.
negative. M1 is square plus C1 plus C3. Yes. Minus C3S plus K2 whole square. You got it?
Mm-hmm.
And what you do is you simply move this here. I just moved this here, right?
I like that. That's cool.
So you can do the same thing here.
Mhm.
Here it will be dy.
And then if you have three equations, you do the same pattern though, right?
Yes.
Okay. Cool.
It's slightly bigger pattern, but
Mm-hmm.
yes.
Okay.
So this, just for completeness, so the denominator will be the same, right? You understand?
Mm.
It will be the same. Okay. It will be exactly the same. The numerator will change. It will be your Z1, Z2 is here, right? So this is 0, all right? And this will be what? C3S plus K2. Right? It will be C F. F of L. Okay, this will be replaced by F of L. You're going to get this.
Well, we can go ahead and pre-solve these for all the different types of systems you can get. Like you can do, you can go ahead and solve one for the one input, one output. You can make one for the one input, multiple.
Right. So it depends on how many outputs are there. If there are multiple outputs, you have to look at multiple input, multiple output system. Okay, and then you'll have 4. If there are 2 outputs and 2 inputs, you'll have 4 combinations. Okay.
It's a lot of math.
Yes. So here, this is of critical importance. Okay.
You said what?
This is of critical importance.
Yeah, I
Both these
understand that.
equations. Okay.
Yeah, I
And what
understand.
you're seeing here is, let's just take a look at what this is. How this relates to control. Okay. Let me spend a few minutes and try to now pay attention. Stop writing.
Now pay attention. So.
Pay attention.
Gotcha.
Now pay attention. Stop writing for a
Good boy.
minute.
I didn't catch what you said.
So think about what you do with regards to control. Okay. You realize that this is the dynamics of the system, right? On the right hand side. You understand? The right hand side of this equation is the dynamics. Is the dynamics function of the input or output?
So that you're asking whether or not the dynamic. I'm just making sure I understood the question. So dynamics are a function of the input or output.
It's not the input.
It's a function input or output. Like you're asking which one.
It's not
It'd
input.
be a function of the output.
Whoa. I thought it was input.
Input.
It's never a function of either input or output.
Whoa.
Dynamics is not a function of input or output. Dynamics is dynamics, right? This will determine the dynamics.
Because there's a constant.
They are, yes. So what we deal with is something called, now keep this in mind, okay? A very critical terminology. LTI systems. Linear time invariant systems. Okay. What that means is, linear means the input-output relationship is linear. You got it? If you do a plot of input versus output, what you're going to get is linear, a linear plot. Time invariant is what? These properties, K1, M1, K2, K3, all those properties of the system don't change with respect to time. You got it? With respect to aerospace systems, are aerospace systems always time invariant?
Yes, if they change within time. They change in due time. That's what you're asking. Yeah, they do.
Yes. So you have to understand that they are neither linear nor they are time invariant systems, or they are time variant. Not all of them. Well, you can say all of them. What changes for an aerospace system?
Position.
Property wise. Don't look at the output. Don't look at input output. The inherent property of an aerospace system. Mass changes, right?
Yeah, fuel. Fuel as you go.
As time progresses, the mass changes. So you cannot just say M1, M2 are constants. They will change as time progresses. You understand? That's a very, very critical component of an aerospace system, that mass changes. But what you do is you approximate. If you want to apply control systems, basic control theory, you linearize it. Okay, you say from this time to this time we are going to assume this is a mass, and then apply it for this thing. From this time to this time this is a mass. We are going to apply that to this thing. You linearize, piecewise linearization. You got it? But you have to understand that whatever control theory, basic control theory we learn, automatic flight control here is applicable to linear in time invariant systems only. Okay, which means all these tools you're learning, the inherent property of the system does not change. So here you have to understand these are the dynamics. Okay, what are you interested in? You're interested in controlling the output, right? By controlling the input. How does the input vary? How does the output vary? What is the output? Output is simply input into all of this. You see it? If I take the input here, right? Output is input into all of this dynamics. Input is predefined, but output is, can be very simple functions, but the output will be a function of the input into dynamics. So if I move this, we looked at this, right? You may define input for n number of systems. That input may be the same. Okay? But will the output be the same? Even in this system, this output is different from this output. You see? Because this output is this input into this dynamics. This output, x2 of s, is this input. The input is the same, but the dynamics are different, which relates output 2 to input. The dynamics relating output 1 to input is different. Does that make sense?
So that F of S is I thought that was
Force.
for
Frequency.
for the first.
But what is happening is, even if it applies to this, when a force is applied, it will impact this. You understand?
Go equals 0.
It is equal to 0, but these two are coupled. Get it? It's not independent. You see x2?
Yeah.
They are coupled.
Oh, so where does the S1 and S2 go in that equation?
S1, S2? There's no
S1 and S2. Like when you're doing Z1 times D, where is the S1 and S2 go?
There is S1.
To the top, the numerator. You did Z1 times D to get that numerator. Right?
This one?
You did Z1 times D, right? So Z1 is the first.
Z1 is this, okay?
Right. Is
D will be 0, right?
Wait, how is Z1?
You're right, actually. It is.
Should be squared or something. It should be squared.
No, Z1 will be f of s, okay?
That's right.
You get it?
Okay.
And
you still, where does the S1 go? That's my question.
this one?
Yeah, where does that go?
This is x. So what you're going to see is,
That's what you're solving for.
you only write A, B, C, D, the coefficients,
Okay.
and replace the coefficients by constants on the right hand side.
Right. So you're saying those are all that's constant, but S is a variable. For
Right.
this.
So here, this you're solving for these two. Keep in
Okay.
mind, they are here, right? You're solving for that.
Okay.
So they come out.
So the FS needs to be there though.
It's in here.
Okay.
What I did is I removed it once I'm done with this, I move it here.
Okay.
You get it?
So f of x is the sum of forces connected to M1.
Hmm.
And that's still the.
It will still have an impact on this displacement. It will not have the same impact as this displacement, but it will impact this displacement.
Just move it.
These two are coupled. You cannot, if you just write one of them,
Mhm.
it's incomplete.
Yeah.
Okay. But try to understand what we are trying to do is, our goal is to control the input. All right. So that
So
we can control the output. We cannot directly control the
Right.
output. You get it?
right. So if you had a multiple input, multiple output system, you wouldn't necessarily ask for it. You would have two different FSs. You wouldn't necessarily ask for x2 over f of s. You could have asked
Yeah,
for
I can ask for x2 over f1, f2 of f. It really depends on. So here you have to look at what your interest is. Okay, what is the problem you are trying to solve?
Yeah,
You get it? Most aerospace systems are these, right?
right.
So you're going to develop the entire dynamics, and then you're going to look at, okay, I want to control position, I want to control velocity. How is it related to all the forces, all the inputs acting on that system?
Okay.
And you're going to try and connect that.
So could you apply this to like a motor, like an engine?
Yeah.
Okay.
Yes. So the engine is going to create what? Thrust, right?
Yeah. So your input. So your f of t would be like the air going into the engine.
Right. So even an engine, within an engine, the engine is, what is the input of the engine?
The air going into the intake.
What is the input for an engine?
It's gonna be the fuel.
It's going to be the fuel. It's going to be the
Oh,
burning
okay.
of the fuel.
Gotcha.
As a result of that, that air is coming. That is a dynamics. That is a aerodynamics.
Gotcha.
Now keep in mind, for aerodynamics and you can of course do the input-output relationship for any kind of dynamics, but try to distinguish. This is analytical dynamics. Okay, this is the mechanical dynamics. So aerodynamics also, if your output will be what in terms of aerodynamics?
Your output.
For an engine
Be thrust.
will be thrust. So it will flip. The fuel will be the input.
Gotcha.
Got it? So here what is happening is you're applying a force, so that now if that force becomes an input, right? Then the output could be something like displacement. So thermal engineer a thermal control engineer will solve the control problem for input-output dynamics of the engine. Okay. A control engineer, in terms of determining the position and velocity of the engine, will take whatever the thermal engineer is giving, okay, whatever input the thermal engineer is giving, and how they are going to determine, he or she is going to determine how the aircraft is going to move for that applied thrust. Got it? So the dynamics, you have to understand here that understanding of dynamics is very, very critical for control engineers. Many of you are going to become control engineers when you graduate. So please keep in mind that electrical engineers do a better job of control engineering, because much of the controls today is electronics. Your strength should be here. They cannot do this as well, because they don't know how to use Newton's laws.
Nerds.
Okay, so your strength is here. to understand and communicate the dynamics. Okay, so don't try to be. You can be good control engineers, no doubt about it. But this is where your safe place is. Okay.
Or you can be a pilot.